lecture 7. Continuing on with the non-ideal op amp. Okay, so for review, a couple lectures ago we looked at MATLAB, how to plot in MATLAB. We also looked at the integrator, differentiator, and the classic feedback system. Okay. We'll be doing a lot of this today, dealing with the loop gain and the open loop gain of various types of op amps, of the 4 types that we had talked about last time, which are right here. So we'll look at this series shunt, shunt series, shunt, and series, and analyze our input, our output, look at the loop gain. We also looked at how to plot Bodie by hand here. And oh yeah, the mistake I emailed you guys about was last time when I just assumed that this was like S, but it's totally not. I look at the zeros and poles, but those are not zeros and poles we're calculating. It's also nonsensical because this is totally imaginary and that's real, so they can't cancel each other out anyway. So that was a super mistake. But anyway, so to do this by hand, you have to get your transfer function into this form where you factor out your coefficient terms, right? And you want to get a 1 plus this j omega over some value. That value turns out to be the cutoff frequencies, like here, here, and here, shown in the plot. So you want to get that for the terms in the numerator, all the terms in the denominator, so you're able to place those where they were, where they're supposed to go. And then everything else that comes out in the front, right here, that is going to be your maximum amplitude. In this case right here is negative 56.5 decibels, right here, and just constant. This part right here. And of course, dealing with logs, everything in the numerator adds. That's why you have this part, which is right here, plus this part, which is right here. And then things in the denominator, you're going to subtract those off, so that's why you have this. You're going to minus this part, then minus that part. And each of these parts right here are magnitudes of that. Okay? And of course, if you look at the magnitude, every time you have this right here, if you look at the cutoff frequency, which is when that frequency is equal to whatever on the denominator, this becomes this j, because that becomes 1, right? And so you have the magnitude of 1 plus 1j, which is the square root of 2, and of course, what's that going to be in decibels?
-3?
Yeah, 3 decibels, right? So if it's right here, it'll be 3. So over here it's like -3. Okay, and so that's why all of these terms at the point of cutoff, you have square root of 2, which is 3 decibels in each one of those. Okay, and those are these points right here. Like right here is going to be 3 above, 3 decibels above. This is 3 decibels below. That's 3 decibels below. If you were to plot it out more accurately, it would cross the 3 decibel point for each one of those. Okay, so so that's the thing with these right here, right? And for each one, you just plot it out. So this right here is this line. This one right here is this green one right here, which has a cutoff of 10. It just keeps going up like that. And remember, the reason why it asymptotes to 0 is because on these things right here, this value gets negligibly small, okay? So because omega is getting very small, and so you just have the magnitude of 1, and that becomes 0 right here. As you're going off this direction, right here, then you're getting 20 decibels per decade. That's what it happens. That's what it asymptotes to. And same with all the other ones. That's why they all look the same, like that. And then you just add them all up graphically to this blue line. Now for the phase, you get the phase, directly from this right here. It's just the imaginary part divided by the real part, right? So there's no imaginary part here, but there's just a real part, so it's the inverse tangent of that. This right here is the imaginary part over the real, ratio of that. Imaginary over the real, imaginary over the real. Now when you plot the phase, what you want to, the difference between here and here is that for these cutoff frequencies right here, those are the inflection points, right? But for the cutoff frequencies here, those are the points where you're at 45 degrees plus or minus 45 degrees. Right here's minus 45, here's plus 45, right there. And then what happens is that, if you're at 45, if you go up a decade, then you have your reflection, which asymptotes to 0. Going down here, this asymptotes to 90. Okay, so for each one, they go out and they asymptote, and they go out, asymptote, and they go out and asymptote like that for each one of those. And then you add them together, and then you get this blue curve right here with them all summed together. Okay. So any questions about plotting by hand? These type of things? Okay, so now today we're going to go over these right here in more detail, and we'll get a better understanding of what it means by shunt, how that's defined, and what it means by series. Because if you look at all of them, it's a combination of series and shunt. Either it's like 2 shunts, 2 series, or series shunt and shunt series. What does that really mean? So we'll talk about that today. And the reason that there's 4 types is because those are the 4 kind of combinations of amplification, right? So here you're just amplifying voltage for your input voltage to your output. Here you're going from a current input to a current output. But here you're going from a current input to a voltage output. And there you're going from a voltage input to a current output. Okay? So that's all the various possibilities. Okay, so here's the concepts we're going to cover. And each of these are just basically so we're going to first look at the series shunt feedback, and then we're going to look at closed loop gain, input resistance, output resistance, and so that's all in 11.5. And then 11.6, we look at the shunt. And the same thing, closed loop gain, input resistance, output resistance. And then series, closed loop gain. So it's just looking at each and every single one of them. Okay, and we'll calculate each one of those so you'll understand how that goes. All right, so here's where we left off last time. And this was Blackman's formula right here. And it's a unified way to calculate impedances, in feedback circuits. So what you do is, on your feedback, you want to, this X can be input or output, or any types of port you're looking at. So you're going to take that port, you're going to look at the feedback, look at the resistance of that port, and you do that by applying a voltage or a current, and looking at the ratio of voltage to current. That's what that is right here. And then for this short circuit loop gain and open circuit loop gain, what you're going to do is at that port, you're going to short it out for this, and then look at the loop, what kind of gain you get in a loop. Or you're going to have this circuit that, the port be open circuit, and then you're going to look at the loop, the gain from that. You plug those in, and that right there is the resistance. Okay, so introduce you guys to that, let's first start off with the series shunt. And here's a few ways to look at that. So here's the basic circuit right here. We saw that last time. Okay, so one way to look at it is basically looking at what's going on inside of the op amp. This version right here is like the ideal version of the op amp. Okay, I mean you could look at it like that, but if you want to analyze, like really characterize that type of system, you want to look at it more like this, where you know that there's some very large resistance between these two nodes right here. And so you can model that by this resistor. It's basically popping it out right here. Okay? And also, the inside of there, you have some output resistance right here, and also a voltage-controlled voltage source right here. Okay? So if you want to, you can actually take this, you can remove this triangle right here, right? And just have all this other stuff without the triangle. Okay, because you basically pulled everything out to really, focus on those things. Also, you should note that this is just like, the 2-port, right? Putting a box around here. These are the output ports. These right here are the input ports. Okay? And then looking at it like this, if you abstract it to this kind of form, this series shunt, which will show is basically, you have the series part, that's on the input, and then the output looks like a shunt. And we'll explain how that is. But that's why it's called series shunt. You're looking at it as a 2-port, and what's going on between these two nodes is something going through series. What's going on through here is something like a shunt. And a shunt is like a low resistance path to ground. Okay? The series is typically much higher resistance. Okay, so one more way to look at it. You can have this this 2-port type of abstraction, right? And also look at it in terms of your feedback loop, because it is a feedback loop. It's an op amp in this case, right? And so you have this VD coming in. This VD right here is like your VID going into your op amp. These things summing together is like this coming in right here, summing to that. So this is negative feedback. That's why you have the negative sign there. Okay? You could look at this amplification going from output to that input at that ratio right here of A. So we can box that all in for the A part. And you have the same thing going, or something similar going back this direction, where here's the amplification of that, which is the input right here, and that's the output. Okay, and that's what we can call beta right there. Now, on this part right here, all I did was take this piece right here and sort of like break it out, right? So this is all ground, right? But I'm just making the nodes available to outside the box. Okay, but it's the same circuit. I'm not changing. I'm not changing the circuit around at all. Okay, so for the series part right here, I want you guys to take a look at the voltage, this input voltage right here. So this input voltage right here is the same thing as starting from ground, going up to this voltage right here, right? So that's V input from your feedback. Here's the feedback network right here. And you're going up another voltage right here, right? So you're going up one voltage from 0 to this part, and then going up some voltage VID from here to here. So if you add both of these together, it should equal VI. Okay? And that's why it's called being in series, because if you have certain components in series, the voltage drops or the voltage gains across each one is series, right? You're just adding these up. Now for the shunt part, it's a little more complicated. I mean, because it may not look like it initially, but the shunt part has two parts in parallel. These are in series, but these two parts over here are parallel. And you can imagine it being in parallel by if you take your, if you apply a load here, like if I set a resistor right here and attach it to the out, that's one line, right, going to ground. Here's the other line going to ground right here. Okay? Or just think of this as like, a black box, but it goes to ground. So this black box, this feedback network is parallel to your load. They both go to ground. Okay? So maybe graphically they're not lined up in parallel, but electronically they're in parallel. Okay? Any questions about that? Like why that's called a shunt? Any questions? Can someone not see how this is in parallel with the load? Very good. Okay, so and this is why we have the voltage at the output right here equal the voltage right here. This from here to here is the voltage across your feedback network, and here to here would be your voltage across your load if you have one. Okay, so let's look at how we calculate closed loop gain, and we'll go into more detail for the first one, and then once you get the hang of the first one, then we'll be able to go through the other ones a little more quickly. So for the closed loop gain AV, remember we had this from last time, right? So this is like our definition of the closed loop gain. Now the thing is it's the ratio of the output voltage over the input voltage, right? So that's the output voltage here, and here's the input voltage. And as you can see, it is closed loop for the feedback going around here. Okay. And we also found out that, and we did some more mathematical derivation. We found out that we can group this part right here into something like an ideal, multiply it by something else that reduces it to a more realistic value. Okay, so this part right here, this fraction here is going to be less than 1. And again, T is the loop gain. Okay? This is the gain between that output and that input, and the loop gain is the gain of this loop going around here, where you have some input here and the output is over here. But it's that ratio. We also define loop gain as A times beta. Remember that? Same thing, A times beta. Something else we did too is we figured out that the ideal version of this was 1 plus R2 over R1. And it was a non-inverting op amp. Okay. But let me ask you this. So do we all understand like why op amps are called inverting, non-inverting? Sometimes. Okay, so if your op amp inverts its input, like if it's just, like some magnification factor, but it's negative, if there's a sign change, then not only did it get magnified or amplified, the phase is 180 degrees out of phase. So when something changes by 100 degrees out of phase, then that's one way to determine if it's if it is an inverting op amp. Okay. If there's no phase change like that, then it's called a non-inverting op amp. In this case, this is not going to be negative. If it's inverting, this would be negative, of course, but this is not negative. Okay. And another way to think about it is, let's Suppose like this. So let's say we have an op amp right here, and we often see these signs there, right? Sometimes you'll see the sign like this. Sometimes you'll see the sign like this. But the math that we apply to this has been basically the same, right? So what's the significance of these signs right here when you apply it to a non-ideal op amp?
Voltage rails.
Huh?
You can't go below your voltage sources. Inverter.
Well, you can. You can go below your voltage sources. Okay, well, let me finish the picture. So you guys, you'll recognize it once I finish the picture, right? So remember, this part goes in here, goes through a resistor, and then comes out like that. Here's our VID, right? And this was a voltage across that VID, right? But using our positive sense, how do we define this VID right here? Like, where would I put the plus and minus signs in this? Like this, right? That makes a big difference, because remember a few lectures ago we were talking about like the importance of having your sign convention in your circuit, because if someone just said, oh, the voltage is, whatever across here, you don't know if the voltage is going from this direction to this direction and that's the voltage there, or does it go this direction and that's the voltage I'm giving you, without a picture of the symbol, right? This gives you your positive sense. So if I said the change of voltage across this op amp was 3 volts, then you would say, okay, well, whatever that voltage is down here, this one is 3 volts higher. But that's because you see the positive sense. On this side over here, where would the plus and minus go on this side?
The other direction.
Yeah. Right? So if I say at 3 volts, difference right there, this down here is 3 volts higher than that. Or you could say this right here is 3 volts lower than that. The sign really matters. Okay? Not only that, there's another reason why. Remember, we have this other part right here where you have your this being magnified by this amount right here. Okay, so the thing is for this part right here, that really does make a difference, because whatever this is going to affect this, right? And it's the same thing over here. Same thing over here too, right? So if this VID happens to be negative, that's going to be, the value you put in there is going to be a negative value, right? So that's going to change what this is. This voltage, if that was negative, this voltage here is lower than this, because it's going uphill a negative amount of voltage. And it's starting at 0. So if it's going uphill some negative voltage, it's going to be negative. Depending on how negative this is, or how positive this is going to dictate what direction of current goes through on that resistor. Okay? So if this voltage right here is negative, and that's more negative, then you know the current's going to go this direction. If this voltage is negative, and that's less negative, the voltage is going to go that direction. Or if it's positive, it's going to go that direction. Okay? So anyway, the reason I'm pointing it out is because that makes a difference in these calculations here. Okay. So anyway, so we actually found this last time. I think the lecture before last. Okay, of what this type of non-inverting op-amp does. Okay, but that's the ideal case. So that's the loop gain. So the next thing you want to do is look at VID right here. Try to figure out what that is. Okay. Now, one way to do this is by using voltage division, right? So, and again, you have to like start thinking, I guess graphically in a certain way, and then mentally change your circuits around so it'll make sense to you. So, the voltage that we're concerned about is this voltage right here. Okay, which is also all along here. It's all this voltage. Okay, now we're starting with this voltage, right? Right here. And so the thing is this voltage right here is, okay, see this resistor RID and this R1? Are these two resistors in parallel or in series?
Parallel.
Why?
They're both running to ground at the same node.
Exactly. That's how you determine things are in parallel. The tops and bottoms have, the voltages of the top parts equal the voltages of the bottom parts. It doesn't matter if they're graphically in parallel. They could be, oriented any kind of way. But if their in nodes agree, then they're in parallel electrically. Okay? So this voltage all along here happens to be this. Well, if this is 0 volts, now going downhill some VID, this is going to be like some negative voltage right here. But anyway, this right here is all the top node, right here for this node and this node. And both of them go to ground. This one goes to ground this direction, this one goes to ground that direction. Okay, so if you wanted to, you could write it out like this, where, here's one path to ground, here's like another path to ground, and one is RID, and the other one is just R1. Okay. And this right here is our key like that. Okay, so let's deal with that. So that's going to ground, and the rest of this, the entire path right here is this RO. Like starting from here, this is RO, and that's in series with R2. And then once the voltage gets right here, it has two paths to ground through R1 and parallel to RID. And that's where this comes from right here. You have the R0, right, in series with R2, and that's in series with these two guys right here, both going to ground. Okay? So that's just by voltage division. Okay? So that's how we find that. And that's really important because we're not really so much concerned with that, but we are concerned with the loop gain. Okay, so remember the loop gain, it was defined in our last lecture as the two gains multiplied together. The first gain going through this first stage, and then the second gain going through the feedback, right? So loop output over loop input is the gain here. Now, so what I did here to try to be a little more clear is not written like this in the book, but try to be more clear. I have these two VIDs. One is the output, and one is the input for the loop gain only. Okay? Because we're looking at the loop gain, T. So that's the gain going around this loop. Okay? And so if you think about it, the input to this loop is right here, right? And the output of the loop is right here. So that's why I have the ratio here. This negative sign, that negative sign is because it's negative feedback. So you want to be careful about your signs. Okay? And so to do this, what we could do is apply a voltage here as your input, and in this case I'm just using Xn. You can put any number here, you know, if you want to, but just assume Xn is some kind of number. It could be 1 volt, it could be 100 volts. It doesn't really matter. It's going to cancel out. That's why. So here's the equation from the last slide. We got this by voltage division. Okay, and what I'm doing is I'm looking for VID because this is my output voltage right here. Here's my input voltage. Now I know you're saying, you know, aren't they the same thing? Well, yeah, they are. But in this type of analysis, what you're trying to do is you're trying to disable your feedback by taking control over it and assigning it a voltage. Okay, and now that voltage is you're sort of like, you know, losing its ability to do, you know, true feedback, right? So you're taking over this, and then you're looking for this. So here's the unknown you're looking for, because that's your output, that's your input. Okay, and so that's why I'm rewriting it like this, where I've taken my VID and I've replaced it with XIN, some kind of input voltage. It could be a number, like I said. So that's why this became that. Okay. Well, this has already been found out over here, right? And I'm just dividing it by IN. And so this IN on the numerator and that IN on the denominator cancel out. And then this is what I get back for my loop gain. Okay. And that was the whole reason of like saying, well, it doesn't really matter what this IN, you put any value in there, but that's what you're thinking about physically, you know, what's going on inside the system. Okay. You guys okay with this? Questions? Okay. So that's loop gain. Okay, so now let's look at the input resistance. And to do that, we're going to look at Blackman's formula. Now, we're going to look at the input resistance, and also, after we do that, we're going to calculate the output resistance. Okay, those are things you guys need to know how to do. Okay, so for the input resistance, here's the input, and you're saying, okay, well, with this being open right here, I really want to find out if I, you know, apply, you know, something right here and look at the ratio, you know, what is going to be this resistance I want to see, looking from the outside. And from the output resistance, we'll look at it from this other side over there. Okay, and remember, so it's RDN plus your loop gain with a short circuit right here. And it's all where you're looking from. You can look from any node you want to. It doesn't matter, you know, it's up to you. And this applies in every single case. Okay? So you're going to short circuit it and find out what your loop gain is. Then you're going to open circuit that and find out what your loop gain is. And remember, your loop gain is going around this direction right here. Okay, so for input resistance, remember this R and D is a resistance of Rn when the feedback loop is disabled by letting A equal 0. So that becomes 0. So if that's 0, then there's no voltage gain across that. It's just, you know, short circuited in that particular case. Okay. So in this case, this Rn is what this sees right here. It sees this resistance in series with this path and parallel with these two guys in series. Okay? So that first resistance right here, and you have this R1 here in parallel with these two guys. find that. Okay, so the short circuit part is that part where I was looking at for the Rn. I shorted out. Okay, and actually in that particular case, if you look at the loop gain going around this path right here, it's actually the same as last time, right? And in fact, on all the things that we'll see, and all of the 4 types of amplifiers that we're looking at, either the short circuit loop gain or the open circuit loop gain, it equals just the regular loop gain, one of the two, and you'll see that. Okay. Okay, so for the open circuit loop gain, you make this open circuit. That means the current going there is 0, and if that's 0, then there's no current going through here. If there's no current going through here, then there's no energy being lost. I mean, so the voltage here equals the voltage there. There's no voltage drop, so that's 0, right? And so with that being 0, yeah, this doesn't matter what that input is going to be anyway. That's going to be 0. So once you have that, here's your Blackman's theorem right there. You plug in your values. We found out what this was by turning this guy off right here. This just became a short circuit. That's where we got this from. And then these other parts here, well, that part's 0, and that part was just our T that we calculated last time. So that's how you use that. And you can apply that to not just these amplifiers, but other kinds too. Okay, and here's the output resistance right here. Now we're looking at output instead of input. So here's input right here. Now we're looking at the output resistance. And we just do the same thing. Okay, so you disable this right here by just shorting it. Okay. And remember, if this was a current source and I want to disable it, it would be an open circuit. But if it was a voltage source, because of short circuit. Okay, and then as seen from here, I have this path in parallel with all this over here. That's what that is. Okay, so I have this is in series with this right here. These two are parallel, going to ground. For the circuit loop gain, right here, for the short circuit, I short that part out of where I was looking at. Okay, what happens here is that this right here becomes 0, right? That's 0, right there. So that becomes 0. And then here's my open circuit. Yeah, okay. Here's my open circuit, so I open that up, and I found out what this is. And again, this part is the same as T that we originally found initially. Like I said before, one of them is going to be T, like the regular T. And then once I have all those pieces for the output, then I just plug it into the same formula. Instead of having in here, now I have out, both cases. And these short circuits and open circuits, I had to calculate from that position right there. Okay, is what I get. Okay. Now let's apply it to the shunt. Okay, this is the trans resistance part right here. And again, here's what it looks like. We can abstract it to like this, where here's like the A part of the amplifier. Here's like the feedback network right here, beta. And you see what I've done here to make beta, right? That's this piece right here. Oh wait, I'm sorry. Is this piece right here, right? I've taken this feedback loop and I just put it on the bottom. You know, so this feedback loop is now on the bottom right here, and its relation to ground is this piece right here. So VIF, your input of your feedback is from ground to right here, and your output of the feedback from here to here. That's all I did. Okay, and then again, you can do your closed loop gain. You've seen this formula right here, and we calculated this in a previous lecture. And of course, that is an inverting amplifier, right? That's, you have your negative there, 180 degrees out of phase. And the reason why is because what's the voltage right here across this resistance? RI. What's the voltage drop across here? Well, okay, so let's come back to that. But yeah, we'll come back to that. But in this case, there's no current going through the RI. I'm just trying to finish. I have like 1 more minute left. So here's like the loop gain right here. And again, I'm skipping steps now. I got this from voltage division. Okay, then I do the ratio of the output to input. I get this right there. For the input resistance, I use the Blackman's formula right there. Here's what I get for RND, right? By turning that off. And here's what I get for T short circuit and T open circuit. That's going to be 0. That's going to be T. Here's what I get for RIN. I just plug those values in. I get that. And for R out, I do the same thing, but to this side right here. And I have a switch here, so if it's open circuit for feedback. R is closed, then it's a short circuit. Or you can just look at the resistance across that, across there right there. And then here's how I'm calculating this part right there. Okay, and the open circuit, you'll find out that it's T. And for the series, here's for the closed loop gain right there. And that is inverting. I'm going to abstract this piece right here, which is ideal to this piece. I'm going to pull out the resistor. I'm going to look at that as the dependent source and resistance. Call this my feedback part. And then I'm going to disable VI for the T calculation. Assume a value for that. And like I said, you can put in 1 volt if you want to. It doesn't really matter. But this is like simplification. This one I'm going to worry about casting out later. But here's what I get for my T value. And then for the input resistance, here's what I get for that. And for the output resistance, this right here. But same steps as before, okay? But different ways of applying it to different circuits. All right. So, any last minute questions? All right, great. I'll see you guys on